Я не вижу часов. Не вижу часов. Нет часов, да? Часов нет. Ну, просто чтобы как-то. Я понимаю, что счастливые часов не наблюдаю. Вдруг кто-то будет несчастлив. Привет. Сейчас не закончится. Да. Окей, нормально. Нет, если я подожду. Закончить я должен в 12:30, да? Или...
Да, еще лучше, 12:29. Okay, so let us continue with the second talk of this morning session, and it would be by Professor Nikita Nekrasov, who will give a course on gauge theories and many-body systems.
So I'm done. Okay, so this is going to be a course on the relation between integrable systems, which I loosely call many-body systems because quantum and classical many-body systems would be probably main examples of this class of integrable systems, and the connections to classical and quantum gauge theories. So gauge theories are interesting for physicists because they describe most of the known interactions of elementary particles, and they're interesting mathematically because, among other things, in recent 40 years, lots of interesting ideas in topology, in particular, and in differential topology, came from thinking about solutions of equations, partial differential equations, which are motivated by gauge theory, and by studying the modular spaces of these solutions and studying homology theory, some intersection numbers and enumerative geometry of these modular spaces, and that led to the advances in understanding the invariance of form manifolds. Also, the related story concerns the invariance of knots and the categorification. So all these mathematical theories were motivated and kind of are developed in parallel with physics developments of gauge theories. Now, I want to present this relation in two ways, because I want to illustrate one of the ideas which is not that old, which is probably is in active development in the last 30 years, and that's the idea of duality. Again, I'm talking about the duality in the physics context. Of course, Duality in mathematics is a very old notion and has lots of incarnations from Fourier transform, from Legendre transform, all the way to Langland's duality. So one of the kind of simpler versions of Langland's duality is what I want to present. So namely, we'll have two types of connections between these two subjects. So one would be the so-called direct, so to speak, direct relation of sort that gauge theory is equivalent to an integrable system. And so this is so this is kind of it's a rare situation when you can analyze the Lagrangian of gauge theory, maybe solve all the constraints represented in proper variables, and see with your naked eye that this is just the dynamics of some particle system, many body system. So this is interesting, but it's sometimes useful actually. We'll see examples of that. How is it useful? And another relation which is kind of indirect is that correlation functions of quantum gauge theory obey classical or maybe quantum equations of some integrable system. So what's the main difference between direct and indirect relation is the relation between the quantization parameters. So in the first case, the Planck constant of gauge theory is the same thing as the Planck constant of the integrable system. So you have literally equivalence of two systems, and so its equivalence is a classical level, and it persists as a result of quantization. In the second case, the quantization of one theory is not directly related to quantization of another. And so what plays the role of Planck constant is not. So they have different meaning, and so this is why it's interesting, because you can maybe say something about the quantum system, quantum gauge theory by solving classical equations of motion of some integrable system, which is simpler, and maybe vice versa. So now, why is it interesting to physicists is that it could be sometimes this integrable system is the same on both blackboards, but gauge theories are different. And so this relation means that there is the duality between gauge theories. And that's what's interesting for physicists, because this relates simple questions on one gauge theory to complicated questions on another gauge theory and vice versa. So this is why it's beneficial to study that. All right. Now, this morning, when I just got off the plane, I got an email from Pasha Esingov, who told me that he already covered all the topics I was about to talk about in this in this lecture course. So, none of the ones he advertised. So I should probably do the same, right? But we have this saying in that repetition is a mother of knowledge. So maybe if I repeat, Pasha, that it will be. At least I'm sure that my notations will be different. So I apologize if you heard this before, and I'm sure you can read it in many textbooks. But all right. If what I'm talking about at the lecture is already known, then we can go over maybe examples which I'm sure Pasha didn't cover in the exercise session. Okay, so now my goal today is to give examples of integrable systems and give you a notion of Lax representation for some of them. And Lax representation, which we'll review, is sometimes the best hint that the integrable system has some connection to gauge theory. So this is the path to gauge theory. Okay. And so my favorite integral system is the Calogero-Moser Sutherland Many system. So it describes particles which move in one dimensions. So one-dimensional so let's denote the coordinates x1, xn. They're indistinguishable. They are non-relativistic, meaning that so the Hamiltonian will be the sum of the kinetic term and so the kinetic term is quadratic in momenta. So I have coordinates x and momenta p, and so there is a symplectic form on the phase space of this system, which is the canonical. So I just give you the system and Darboux coordinates x and p. Now, what is the phase space of that system is a bit tricky. So let's start by, let's take r to the n without diagonals and take the cotangent bundle to it. And now I said that my particles are indistinguishable, so it means that the configuration space is not really the set of positions of my particles, but the set of modular permutations. But it's better to make the symmetric group act both on coordinates and momenta. And so we'll take the quotient of that by the action of symmetric group. And so the Hamiltonian, the classical Hamiltonian, has a parameter nu squared. And so there is a potential which describes the repulsion between the particles if nu squared is positive. So if nu is real. And so because of this repulsion, the configurations of finite energy don't allow particles to touch each other, to see the top of each other, and that's why I deleted the diagonals. Now, so this is so it's a Hamiltonian. We can write equations of motion. And remarkably, these equations can be packaged in the equation of Lax form. With the where L is the so L is going to be an n by n Hermitian matrix with momenta sitting on the diagonal and nu times of diagonal. So so this is antisymmetric, but I multiply it by I and make it Hermitian. And so the claim is that there is a matrix A which depends on P and X, such that the time derivative of this operator, according to these equations, is actually a commutator of L with that matrix A. It's a good exercise, actually. It's not difficult to find it explicitly. Now, what it means that it implies that eigenvalues of L are constants of motion. Now, what are these eigenvalues? Well, if you imagine that, so your particles, since they repel, so they, when you wait sufficiently long time, they'll probably end up being very far from each other. And so in the limit when time goes to plus or minus infinity, up to some permutation, so the representatives of my particles will be very far apart, and so this off-diagonal term can be neglected. And so these eigenvalues are essentially the momenta, the asymptotic momenta. Plus minus stands for time going to plus or minus infinity. So the way how you order this momenta, it's depends on your, the way you do your accounting. You can order them according to the positions of particles. So the eigenvalues, of course, are defined up to a permutation. So the individual eigenvalues don't need to conserve. I mean, the individual eigenvalues at plus or minus infinity in time don't have to be equal. They can be permuted. But as a set, they are the same. So the eigenvalues are not very useful functions of P and X because they are solutions of some algebraic equations. You can form polynomial functions of momenta and rational functions of coordinates by taking the powers of the operator L and taking the trace. And so these will be also, these are integrals of motion. Now, I claim that this is the simplest example. Maybe the simplest would be the free particles when nu is equal to 0, but it's one of the simplest examples of gauge theory. So let me explain that. So this is going to be the simplest example of a direct relation between gauge theory and integral system. So what I'm going to review is known under different names. One of the names is the projection method of Alchanevsky and Perelon. And so in this method, one interprets the seemingly non-trivial motion of seemingly non-trivial evolution if I divide by k, then this Hamiltonian actually turns out to be H2. So the seemingly non-trivial evolution of the system is actually a projection of something very simple from a larger phase space. And so there is a large phase space hidden in this problem, which is the cotangent bundle. I mean, it's a vector space to the Lie algebra of group UN. So this is the Lie algebra times times the projective space of dimensionality n minus 1. Actually, we can do it even, we can make it even, let's do it even simpler. So let's just, for fun, consider the following simple symplectic manifold. It's just a vector space. It's a vector space of dimension. Sorry, what I meant here was Rn, of course. Later we will complexify certain things, so that's why I'm slightly confused here. Okay, so it's a vector space, symplectic vector space. Of dimension 2 because it's symplectic manifold, and then n squared plus n. Okay. So let's parameterize it somehow. Let's call the elements of the Lie algebra of UN. Let me call them I square root of minus 1x. So x will be an n by n Hermitian matrix, and the conjugate momenta I will call square root of minus 1p. So p is also Hermitian matrix. So these are n by n Hermitian matrices. And well, I have a vector, let me call it vector v, and the covector w. So v is a vector, w is a covector. So that's my space. And on this space, I want to study two things. So first, I want to introduce very, very simple dynamics. So the way I represent things, these are conjugate variables. So P is conjugate to X and W is conjugate to V. I hope it's clear. Conjugate in the sense of a symplectic form. Omega is trace dP dx plus dW dV, where I understand that you contract W with V as covector with vector, and here's a trace. Okay. And so let me define the Hamiltonian to be simply trace of P squared. So it's very simple Hamiltonian. And the time evolution it generates is that so at this point it's not clear why do I need this vector and covector. They just go for the right. Nothing is going on with them. So this part we can actually generalize. We can take any Casimir built out of P and consider simultaneously evolution with respect to different times. In principle, you can take K to be arbitrary, but the evolutions which will be generated by HK when K is greater than N can be reduced to the evolution which is already covered here. All right, so this is very simple. It's a trivial, just free motion, but in a large space. So matrix is just changing this way. Now I want to, the second ingredient which I want to introduce, and that's essentially what gauge symmetry is about. I want to say that my problem has a symmetry, and I want to perform the so-called symplectic quotient with respect to its symmetry. So symmetry. The symmetry will be generated by the group UN. And in order to see how it acts, well, so P, so G will send so let me combine my vector and covector into a complex vector. And so P, X, and Z go to X. So the only thing which Z does, it transforms under the action of the unitary group. So purists would have said that there is a little bit more structure which I used here. And so so T star of Rn was actually C to the n. And so that C to the n is the space with Hermitian structure, which is what my unitary group preserves. So that's the second I said that I'm talking about UN, it means that there is a space with a Hermitian structure. So that's T star to the n. Right. Okay, so it's a symmetry, and it's a symmetry which preserves the symplectic form, and which is an exercise, by the way. And of course, it commutes, it preserves my Hamiltonians, and so it means that if I take a simple motion in my large phase space, so this is large phase space. So here I have a basically straight line motion, but then I have the action of the group. So these are G orbits. So the small phase space didn't denote it, so let's call it. So this is P large. And this is P small, which is P large symplectic quotient with respect to G. I will in a second remind you what it means. So on the small phase space, this trivial motion may now look complicated because I'm performing identifications with respect to the group action. You all know this. This is what you experience when you try to stand on rotating table. So, in other words, I mean, the simplest example of this construction when n equals to 2, we can actually discuss. So just take a free motion of a particle in the three-dimensional space. So R3 is essentially, it's a Lie algebra of SU2. So we remove center of mass. And then, so this is a free motion, R. And then try to project it onto the quotient of R3 by the action of the group of rotations. So it means that your invariant is the radius, the distance from the origin. So now, if you look at the time dependence of this object, well, it looks like, so if time goes by, this is R, which is strictly positive, well, it will have some shape. So it looks like now the particle which is represented by the radial coordinate of my free particle in 3 dimensions experiences some force which repels it from the origin. So that's the centripetal force which you, yes. Yes. So we'll get there. So you see, in the ordinary world of spaces with symmetry, the normal thing to do is to take a quotient. So you just take equivalence. You go from the space to the equivalence classes, where you just contract the whole orbit to a point. But we are now in the world of classical mechanics, where we deal with symplectic spaces, symplectic manifolds, and if you just take a quotient of a symplectic manifold by the action of the group, the quotient is not a symplectic manifold. So there is a procedure which remedies that, and so let's review this procedure. So there is something called the moment map. In fact, I recently checked because Pasha Wigman, who is probably here, was telling me that it should be a momentum map, and I was arguing with him, and then it turns out that he was correct. So in English, it should be called a momentum map. It was moment in French, because in French the momentum is impulsion, just like in Russian. So but somehow in translating between languages, things got confused. So the moment comes from angular momentum, and so it should be a momentum map. And so this map is the map from this large phase space to the space dual to the Lie algebra of the group, which acts on this space, which acts by preserving symplectic form. And so what this map is, it's sort of a collection of all Hamiltonians which generate the symmetry in question. And so let's instead of explaining what it is in general, let's just compute it. Let's just compute it in this example. Maybe I can remind you first what it is in this example of a particle moving in three-dimensional space. So the particle moving in three-dimensional space has the six-dimensional space as a phase space. So there are coordinates and momenta. So these are the. And the symmetry in question is the group SO3, which rotates P and R. And what are the generators of that symmetry? Well, these are, in this case, precisely the angular momentum components. And that's the example of the moment map. So this is the map from the six-dimensional space to the three-dimensional space, which is dual to the Lie algebra of SO3. So this is an example of momentum map. So what it is here, so we need to, first of all, compute the infinitesimal version of the symmetry transformation, and then ask what generates these transformations. And then, so if I take G to be close to identity, so psi is now on the Lie algebra of UN, then the kind of a vector field which corresponds to this element of the Lie algebra psi, evaluated it, is well, it's just the commutator of P with psi, commutator of X with psi, and it's minus psi. Let's see. So I said that this vector field preserves the symplectic form, so it has to come from some Hamiltonian. So there is a Hamiltonian which generates this vector field, and the vector field is linear in psi, so the Hamiltonian will also be linear in psi. And so this will be the part which generates these transformations. So what I mean is that by that is that if I differentiate H with respect to X, I should get minus this quantity, and if I differentiate with respect to P, I should get this quantity. So if I didn't make a mistake, that's what I should get. And then this part is generated by a rank 1 matrix Z tensor Z dagger. So if Z is a vector with components Z1, Zn, this matrix is as components zi times zj bar, ij from 1 to n. So this guy is linear in psi. Therefore, it comes from some. So it means that it's a pairing of some covector on the Lie algebra, which depends maybe in a nonlinear way on p, x, and z with psi. And so this part is the moment map. This is mu p, x, and z. So mu now, there is one important correction, which is that this map, of course, this map is defined not uniquely because the Hamiltonian. So the relation between the vector field and the Hamiltonian is not one-to-one. So the vector field associated with the Hamiltonian is the derivative, the differential of the function, the derivative of the Hamiltonian, to which we apply the inverse of the symplectic form, the Poisson bivector. I don't know how you want to put it. I'll just apply. So now you see there is a derivative here. So if h, if my h and your h differ by constant, we'll get the same vector field. But if I know the vector field and I want to reconstruct the h, I can only do it up to a constant. So, so this definition that will reconstruct mu of psi up to a constant, which is linear in psi. And in general, so there is this little bit of cohomology problem, whether one can adjust these constants in a nice way. A nice way is where the Poisson brackets of the moments evaluated at different elements of the Lie algebra agree with the moment evaluated on the commutator. So this is the equivariance, G equivariance of moment map, which is usually required. And so that restricts the freedom in choosing the constants, but still leaves some room for this constant if your group is not simple, particularly if it contains a center. And so here, in this precisely, in our case, UN contains a center, and this center allows me to add a constant, which I will call mu, times the unit matrix. Is there a question? Okay, okay. I was hoping that you will point a mistake because I already tricked you. I made a mistake just so. Well, this is Hermitian. This is anti-Hermitian. So there is an I somewhere missing. Now, this vector product of P with R in the three-dimensional case is the commutator of two 3x3 antisymmetric matrices expressed as a vector. So this. Okay, so now we almost ready to project. So what do we project? So we this symplectic quotient, we take the preimage of 0 of the moment map. And because of the equivariance, so this is why I made this speech about equivariance, this is a G invariant submanifold. And so we divide it by G. And we claim it that this is symplectic. This is symplectic. well, it's a manifold if the 0 is a regular value of moment map, which is the case when nu is non-zero and positive. So the projection. So now we can discuss what's going on with projection. So let's solve the equation. So let's solve the equation u equals to 0. In other words, p commutator x is equal to square root of minus 1 nu times unit matrix minus z times z dagger modulo G symmetry. So modular these transformations. Well, since P and X are Hermitian matrices and my G acts by conjugating, I can find the representative in the G orbit of the triple PXZ where X is diagonal, for example. So there is a representative. So let's fix that representative. It's still leaves us with a little bit of symmetry because there are still transformations of this form which preserve the fact that X is diagonal. And so this reduces G to the product of U1 to the N, so diagonal matrices. And there are also permutations. So there are transformations which will permute the eigenvalues of X. So we'll deal with them later. Now let's solve the this equation. In this basis, when X is diagonal, let's look at the, well, we can just write this matrix now. P X ij is P ij times Xi minus Xj. And this matrix, so this should be equal to square root of minus 1 nu delta ij minus zi zj power. Now, if I equals to j, the left-hand side vanishes. Therefore, nu should be equal to absolute value of zi squared for any I. So now our vector z has entries which all have equal absolute value, square root of nu. So I'm assuming that nu is positive. It's obvious, like if you take the trace of left and right hand side, that that if nu is negative, then you have no solutions of this equation. So nu is positive. Now I'm using those remaining transformations, which so G of the form so G, which is just a diagonal matrix of phases, which allows me to make Z to be square root of nu, so make them all real positive. So that now reduces. So that reduces the group of remaining transformations, reduces them to just permutations, because they will not change this vector z. They will not change the fact that x is diagonal, but they will still act. We will permute eigenvalues and we'll do something with p. But now we can solve for p. So p from this equation. So when I equals to j, the diagonal part of p is not defined, is not determined because it's multiplied by 0. So p can have an arbitrary diagonal part. And for when I is not equal to j, then just divide the right-hand side by xi minus xj, and we'll get the solution. So square root of -1 nu delta ij minus 1 xi minus xj. So maybe I erased the formula, so it's okay. So maybe I made a sign mistake. Okay, so what's the conclusion? The conclusion is that now, if I parameterize my space of conjugacy classes, if I parameterize the orbits of the group action by diagonal x, or by eigenvalues of x, if you like, in this basis when x is diagonal, p has this form, and now the motion looks non-trivial, because now so x1 of t, xn of t are eigenvalues of x1, so this is the diagonal matrix xi of 0 delta j plus, let's say I do only the flow for the quadratic Hamiltonian, and so then this is pi so well, it looks non-trivial. So now we I mean, if even that is not exact. So I'm not sure what I'm trying to say. So what looked simple, once again, so what looked simple x goes to x plus t p, p goes to p. Now it's complicated because now I keep performing the compensating transformation. So now I accompany my simple motion with transformation g, which depends on t, in such a way that this matrix is diagonal all the time. And so now it looks like a very non-trivial dynamics. Now, where is the gauge theory and gauge symmetry? Well, this is the gauge symmetry. So this is gauge transformation. So it's a symmetry transformation which depends on time. And the way to represent it by Lagrangian, from which we will derive these transformations by variational principle, is to start with the usual Lagrangian associated with the symplectic structure and the Hamiltonian. So dot means derivative with respect to time. And then I can write similarly z dagger, z dot minus trace p squared plus. So if I stopped here, that would be just a Lagrangian describing the free motion which we discussed before. So here the gauge symmetry is not implemented. It's here this Lagrangian describes the system which has a symmetry, but that symmetry maps one solution to another solution. If I want to declare the symmetry as a gauge symmetry, so I want to reduce the number of degrees of freedom, I introduce Lagrange multiplier, and it is traditionally denoted as A sub t times mu. So, trace. In fact, more canonically, I could have written this as mu times A sub t. So A sub t, it's a new field, new variable if you like. It's actually one form valued in the Lie algebra. It's one form on time, so on t. T is my parameter on its time. So it's one form in time direction, and right. So A sub t is the one form valued in the Lie algebra of G, and mu, remember, was the map from the phase space to the dual space to the Lie algebra. So they pair naturally. So it's mu of actually right, mu of p x z evaluated on A sub t. Now there's a little bit of adding oranges and apples here, because so this term is naturally, it's a one form on time, so you can write it as p dx. And so this is also one form, and the only term which requires, which actually depends on parameterization of the trajectory is Hamiltonian, so we put dt here. And instead of writing Lagrangian, we will write an action. So the point is that now, if I take this functional on the space of time-dependent fields, so p depends on time, x depends on time, z dagger all depend on time. So S is a functional on maps of R, or maybe an interval valued in a large phase space, times one forms on R valued in the Lie algebra of my gauge group. But now, oh miracle, this functional actually has a symmetry. And so we can actually divide it by the action of the group of maps R to group. And what is the symmetry? Well, it's the symmetry which I wrote here. So it acts on the variables pxz in this way. But now, so if this is now a trajectory. So G is also, so G is now allowed to depend on time. So, so if you take this action and perform this transformation, you will find that it is not invariant under these transformations. It is only invariant under transformations when G is time independent, it's constant. However, the point of adding this term is to make the whole thing invariant, provided now that A sub t transforms in this way. And so this is the first glimpse of gauge invariance. So A sub t is actually a connection on a trivial G bundle over the line, the timeline. So so this many-body system is actually the simplest one-dimensional gauge theory. It's a gauge theory whose space-time is just time. There is no space, but the variables have the original variables have some metric structure, and so that it's sort of the hint that maybe you see A sub t. So it is valued in the Lie algebra of the unitary group. So it's one form of these are just n by n matrices, like n by n Hermitian matrices or anti-Hermitian matrices, and so are p and x. So it sort of suggests that maybe in the better world, p and x, or maybe both p and x, also become the components of some gauge field. Maybe now it will be the gauge field on a higher dimensional space, and then that would mean that this system has some generalization or deformation in which these extra dimensions will be visible. And so that suggests that one should study not just one should study deformations, maybe integral deformations of this Calogero-Moser system. When I say this Calogero-Moser system, I mean the rational Calogero-Moser system, because this potential is given by a rational function. And indeed, so just write it down. So maybe P and or X are also one forms, also components of a gauge field, of a connection. So we have time. So this is A sub t. That's Lagrange multiplier for the moment map. And maybe there are additional space directions, so that maybe A sub x is going to be x, and A sub y is going to be p. And so that would suggest that the Calogero-Moser system, rational Calogero-Moser system, has deformations, maybe integral deformations. Well, the answer is yes. So all these scenarios are realized, and they correspond to a plethora of generalizations and deformations of this model, which we'll encounter. So 3 generalizations. So there is rational Calogero-Moser, and there is a trigonometric Calogero-Moser, also known as Sutherland. And then there is relativistic. Actually, there are 4 generalizations. And there is elliptic. relativistic rational known as rational Roisenachs. Schneider, trigonometric Roisenach-Schneider, and then there is actually elliptic Roisenach-Schneider. And I'm out of space, and it's a good thing because below are conjectures and still unexplored territory. But these arrows, they correspond to actually uncovering additional dimensions of space. And so these models correspond to different gauge theories living in different space-time dimensions. So this thing corresponds to two-dimensional Young-Mills theory. This thing corresponds to three-dimensional Chern-Simons theory. This is some kind of hybrid topological holomorphic 2D Young-Mills theory. And this is so-called four-dimensional hybrid topological holomorphic Chern-Simons theory. Okay, so these are words. What do I mean by them? And, where do we go from here? So let me explain maybe. Let me explain something simple. So trigonometric Calogero-Moser Sutherland. This is the system where your particles now live on a circle. So R becomes R mod Z. So we replace the rational function for some reason, it's better to write it this way. So, okay. So you can think of this as of the system where the symmetric group, which was permuting particles, got promoted to a affine Weyl group. So in addition to permutations, you also have shifts by the period. So the period being 2 pi. Yes, 2 pi. So 2 pi z. Yes.
Are talking about functions of particles, symmetries, and affine Weyl groups. So certainly you should get lots of representations of ray groups, Coxeter groups, and many similar things, right?
Yes. I mean, the verb should has kind of too much of imperative for this time of the day. I mean, I didn't even start talking about representation theory, which is behind this story, because you see, this is for the moment is classical mechanics. So the representation theory usually is associated with quantum systems. So in quantum systems, we would promote maybe P to an operator of d by dx, and we'll be looking for the eigenfunctions of the corresponding operator. Yes. Yes. It was not, right. So where was it? Oh, sorry. Okay, so this is, just look at this term, pdx. So d means time derivative. So if you apply the transformation, I mean, students should do it at the exercise session. So if g depends on time, so dx on g, and so we will get a correction term. And this correction term will be precisely mu, like commutator p with x. And so that's why you need the inhomogeneous part. So that's kind of the simplest way in classical mechanics to understand where the origin of the long transformation property of gauge fields, of connections. They're not just one forms, they're connections. All right, so yes, so there is an old construction of Kazhdan, Kostin, and Sternberg, which explains how to get this system by a projection method. In their construction, you replace the Lie algebra of UN in this large phase space by the group, and repeat the whole story. This is not the way to see the emergence of additional dimensions. In order to see additional dimensions, you promote everything to loop space. So promote UN to loop algebra of UN, or precisely to the central extension of the loop algebra. So these are now functions of an additional variable. Let me call it x. So x belongs to a circle. This is different font. This is not that x. And so these are, okay, so this is, so E of x lives in the Lie algebra. And C is just a number. And so it's a, so there is a structure of Lie algebra on the space. So you take a pointwise commutator of Lie algebra valued functions. So that would be just what's called a loop algebra. Sorry, this is. And then, but the center. So the C1, C2 they disappear from the commutator, but something appears instead. And that's the integral over the circle trace E1 dE2. So again, a very useful exercise for students is to check that this formula satisfies Jacobi identity. And so now the dual space actually consists of interesting beasts. So there are so EXC, and the vector space, which is dual to the Lie algebra of the Cosmodi algebra of the current algebra, is actually the space of differential operators of first order, sometimes called lambda connections, but physicists call it K connections because there is a K, where K and C are real numbers. So E and AX are G-valued functions on S1. And the reason I wrote I combined A sub x and k into the first order differential operator is that you verify that the coadjoint action, so the action on, so A sub x pairs with E. So the pairing is integral over S1 trace E A sub x dx plus kc. So the claim is that if you act on the Lie algebra by the Lie algebra in the adjoint representation and compute the coadjoint action so that the pairing is preserved, then this coadjoint action will act on A as on the differential operator. And so when you integrate it to the at the level of the group, the loop group action on this quadruple is so it's pointwise conjugation of E and gauge transformation of A. So K is invariant, and C actually transforms in a way which I will not write. But it's computable. It's not a big deal. So so from that, this is we should think of this E is an analog of P, and X and A sub X is an analog of X. So now the commutator P of X gets promoted to the covariant derivative of E. So there is one step here which is not very motivated, but I will just do it. K is kind of an inconstant of motion, so I will fix it to be 1 once and for all. And so then the commutator will become just covariant derivative of E, which is the derivative plus the commutator. Now, what happens to this term ZZ dagger, or nu times 1 minus ZZ dagger? This is part of what, sorry? So this is the moment map for the action of the group on the cotangent bundle to the Lie algebra. So this is the moment map. So mu was that. So this is the part of mu which came from T star of the Lie algebra, and now the same part becomes that. So the new term is the derivative acting on E. Now, this strange notation is that in physics, this is called electric field. That's why it's called E. And this is called, vector potential. And this particular combination, so this derivative, the covariant derivative of electric field, is sometimes called the Gauss law. This is Gauss law in one space dimension, so it's maybe not that recognizable. We normally discuss Gauss law in 3 dimensions, and we measure it by the number of flux lines, force lines of electric field piercing some surface. So we measure it by divergence of the electric field. So this is the one-dimensional divergence of electric field in a non-abelian case. Now this term comes from, remember, we had this copy, this n-dimensional representation of the unitary group, which we used for one thing. The use of that was when we went to the gauge, when we found the representative where diagonal representative of x, so fixing the gauge when x was diagonal did not completely use all the symmetry we had. So there was a little bit of symmetry left, and that was of diagonal transformations. And so we needed this vector in Cn to absorb this remaining symmetry. So something similar happens now in this infinite dimensional case. So the analog of x being diagonal is now a sub x is diagonal and constant. So these are constant respect to x. Let me say a few words about this representation. This is known as Flaquet-Lyapunov theory. So the question is, if you have a function, if you have a matrix valued function, so n by n matrix valued function on circle, so a sub x, and I studied up to transformations of this form when G is a map, it's a periodic function, periodic group valued function. So what is the normal form? I mean, to which form can I bring this function a sub x? So what is the canonical normal form? And so I claim that you can make a sub x diagonal and constant. So all the all the x dependence can be absorbed in G. And so this is Flaquet-Lyapunov theory. Well, basically, you try to solve the equation. So you try to make a 0. So you try to make a vanish completely by this transformation. Well, that would require solving an equation a equals dgg inverse. I mean, I want to kill a. That means that find G such that A can be written in this form, right? Because Lie algebra valued, yes, Lie algebra valued. Well, n by n matrix. It's a Hermitian matrix. Just divide by I. Anti-Hermitian matrix. Okay, well, how to solve this equation? Well, just means that I need to solve the equation dxg equals ax times g. So it's a first order ordinary differential equation. You give yourself some initial condition, and you just solve. What's the problem? The problem is that by the time you come back, you're in a circle. So you start with g, let's say it's 0. You can choose anything you want, and then you solve. So g of x will be path-ordered exponential. Sorry, path-ordered exponential from 0 to x integral a sub x. So this notation means Dyson series. So it's 1 plus the integral plus order plus iterated integral. So by the time you came back, you need not arrive at the same g you started with. And so that's the abstraction to finding such g. So the abstraction to kill A is holonomy, monodromy. So it's path of exponential. So this is some, so if I start at point 0, so it's some group element which has eigenvalues. And so the eigenvalues of G, essentially the logarithms of eigenvalues of G is what enters here. So the e to the 2 pi I x1 actually maybe okay, so if 2 pi's are there, then there's no 2 pi here, and there is 2 pi here. So sine squared pi xi minus xj. Okay, so you can find G such that so you cannot find G such that dg will be equal to A times G, but you can always find G such that dg equals A times G minus G times the constant diagonal matrix. And so that way you will undo this holonomy. So okay, 3 minutes left. Right. So so if I find the gauge, so if I make a representative for A to be constant diagonal, there are still transformations. There are still transformations of this form which will preserve the fact that A is diagonal, but they will change the eigenvalues. So if you take now the G of the form e to the 2 pi I and 1, sorry, I 1x. So remember, x changes between 0 and 2 pi, and my G should be periodic. So that forces numbers n to be integers. And so that will shift. So such transformation applied to A, which is diagonal, will shift xi by an integer. So this is the affinization of the Weyl group, which I was talking about. And so it okay. Now if you sorry, yes, I forgot. So I needed to explain this thing. So So these are transformations which change eigenvalues, but there are also transformations, so G of the form when theta is a constant. So these transformations will not change A at all. And so we need the analog of the Z vector to absorb this remaining symmetry coming from those vectors. And we need just finite dimensional, just one vector space C to the n. We don't need fields. We don't need x-dependent functions varied in C to the n. And so that's why, in the end, it turns out that the contribution of this, so the analog, the loop analog of this momentum, this term in the moment map becomes delta function times nu times 1 minus z dagger. So, so now I've said everything. So if you combine this plus that, set it to 0, solve the moment map equations, and then compute the Hamiltonian, which is the integral of the quadratic Casimir applied to the electric field, you will get that Hamiltonian of Sutherland. So this is how, okay, so in a few examples, I told you, I showed how one can see directly how gauge theory, simple gauge theory, is actually equivalent to a classical mechanical system of interacting particles. So next we'll discuss various ramifications of this story. We'll go from two-dimensional Young-Mills theory living on smooth manifolds, maybe on cylinders or on pairs of pants. We'll generalize this story to Young-Mills theory on forms. And we'll get lots of integrable systems. I don't know what the spine of any manifold is. So I'll explain what I mean by form. Maybe, again, maybe it's not what other people knew. I actually, sorry, form is something, it's a word that somebody put it in my mouth. I call them origamis, actually. So these are spaces with corners, junctions, and all kinds of similarities. Okay, my time is up. So see you all in the afternoon.
Any questions?
Yes.
My question is it possible to write just this action and now start from the general equation of the production and obtain this?
Okay, so maybe the impression that it was heuristic was because I was doing it in a, I mean, this is completely rigorous. It's well, it's what can I say? So there are two ways of thinking about it. So one way is just straightforward generalization of an analysis from fine-dimensional algebra to Cosmode algebra. And another way starts by saying that let's take the standard action of Young-Mills theory, which I didn't introduce, write it in the canonical formalism, so write it as a pass from Lagrangian to Hamiltonian. Young-Mills theory in the presence of sources. So there is a there's an element here which corresponds to this delta function. It means that you have what's called the Wilson line in some representation. So this is the straightforward analysis of the Gauss law in two-dimensional Yang-Mills theory in the presence of a single Wilson line. And so tomorrow I plan to discuss what happens when you have several Wilson lines and maybe junctions and more general things. Now, the secret of this is, of course, that in two dimensions, Yang-Mills theory has no propagating degrees of freedom. So it is not very surprising that what is called two-dimensional gauge theory is actually equivalent to something which is actually one-dimensional. One-dimensional meaning it's just this, classical mechanical system. There is time and there is no space as such. These degrees of freedom, these coordinates of these particles, are precisely the eigenvalues of the holonomy of the dynamical gauge field around the circle. And so these other examples which I mentioned in this table are similar in that way. So these are all theories which have essentially no local degrees of freedom, but they have global degrees of freedom. So depending on what space-time manifold you put them, you will get quite non-trivial mechanical system, classical mechanical, quantum mechanical system, depending on whether you study classical theory or quantum. In the last three lectures, we will be discussing much more sophisticated relations between integrable systems and gauge theories, where the theories will actually live on high-dimensional spacetimes. They will have local degrees of freedom, but there will be an additional structure. There will be a nilpotent operator acting in the space of states of the theory, and the cohomology of this operator will turn out to be the space of states of something finite dimensional. And so that's this indirect relation.
Okay. More questions?
Yes. Yes, they will appear in Lagrangian, but they will only live at the point x equals to 0. So the variables z and z dagger live only on this blue line. So they continue living in time, but they don't live in space. They live at one point in space. So Wilson line. So Wilson line represents if you imagine a very heavy charged particle, so heavy quark, like top quark is very heavy, you can actually make it follow classical trajectory as opposed to light particles, light quarks, which are all over. You cannot squeeze them you cannot pinpoint them at that point in space. But heavy objects can be localized in space, and so that's what this represents. Of course, there is a bigger, better world where we sum over all Wilson lines, so we have and make them dynamical. So that's why I will consider more general situations when they have a dynamics of their own. And so then the sum over all lines can be represented by another field. So that would be now in non-trivial theory, two-dimensional QCD, for example. So Yang-Mills plus charged matter. So that theory in itself is not solvable, but if you expand it in the number of particles in each sector, it can be approximated at least by an integrable system, which is of that kind or some generalization.
Okay, I think we should probably thank Nikita again and take a lunch break.